Hi everyone, I hope this video finds you well. In today's video, we're going to be investigating the proof technique known as a direct proof. Now, this video is part of a series of videos introducing you to mathematical proofs. Hopefully you've already watched the preceding video to this, which was an introduction to mathematical proofs that talked a little bit about what exactly a mathematical proof is, some of the notation and language that we use in mathematical proofs, and had some comments about the sort of style aspect of how to make a good mathematical proof. In today's video, we will actually be focused on learning the first major technique that can be used for a mathematical proof, which is aptly named a direct proof. So what is a direct proof? Well, a direct proof, right here, we have a sort of rough definition. A direct proof is a mathematical proof where we proceed directly from the given assumptions via logical steps, mathematical operations, or known properties to reach our desired conclusion. So that's basically saying that a direct proof, as its name would imply, is one where we start from a set of given assumptions, work from those assumptions, directly moving forward step by step using either logic, mathematical operations, or known mathematical properties, and eventually reach our desired conclusion. Because of this, one of the biggest challenges in a direct proof is usually simply rephrasing the written statements or written assumptions into mathematical statements. Since a direct proof basically involves just moving forward directly, step by step, what that means is that we really have to concentrate on the idea of how to translate the assumptions that were being given, or the mathematical or the written statements that were being given, into mathematical statements. So how do we do that translation? Well, we can talk about that right here. Translating written statements into mathematical statements hinges on having good definitions of mathematical concepts. And this really shows how this idea of a proof technique can be applied in lots of different math courses. You might be looking at this series of videos in relation to, say, like a Calculus 2 class, a discrete mathematics course, a differential equations or linear algebra course. What we're talking about here with mathematical proofs applies to any branch of mathematics. However, in each of those branches, we're focusing on very different concepts. And that means that to apply the technique of a direct proof in those different branches of mathematics, you need to make sure you have a solid grasp and solid understanding of the definitions of the different concepts or terms or vocabulary being used in each of those branches. Finally, we want to make just this comment, and this is something that applies really to every proof technique, but since direct proof is the first one we're discussing, we'll mention it here. At the beginning of a direct proof, we want to make sure that we have a clear statement of what we need to show. And we often abbreviate that as our NTS, our need to show. And this is really important because this sort of ties back into some of the comments from the previous video about sort of style, right? A need to show is providing the reader with a translation of what do we actually need to accomplish to logically finish this proof, right? It's sort of saying something like, we have our goal, and our goal is probably written out in English. We're going to translate that goal into a mathematical statement. And then when we reach that statement, given our series of steps, we have really shown the reader, hey, we told you we needed to get to this point, we've gotten to this point, and therefore we're done. So you're basically showing your reader the target that you're hoping to hit by the end of the proof. And then when you do hit that, that leaves no argument that you haven't completed what you needed to complete. So a need to show and a clear translation of that need to show is an essential part of having a good direct proof. So in summary, right, a direct proof is one where we will be moving from assumption to conclusion directly via logical steps, mathematical operations. That means we're going to focus in these upcoming 3 examples on the idea of rephrasing written statements into mathematical statements. We're going to focus on making sure we understand the definitions that are necessary to make those translations possible. And we're going to make sure that we always have a clear need to show written out before we start the proof so that when we reach that, we know that we've finished. So, without further ado, let's take a look at a couple examples of direct proof. So, here's our first example we'll talk about. We're going to prove that if x is an odd number and y is an odd number, then x plus y is an even number. Now, if we think about that statement, right, we can confirm it in a couple basic cases. We can pick an odd number like 3. We can pick another odd number like 11. And we can say 3 plus 11, that's 14. Oh, and that is an even number. That's a confirmation of this statement. But it is definitely not a proof of this statement, because that was only talking about this statement being true in one particular situation where x was 3 and y was 11. We need to prove in generality that no matter what odd number you choose for x, no matter what odd number you choose for y, that the sum x plus y is guaranteed to be an even number. That's what's going to make this a mathematical proof. So let's go ahead and try to do some translation before we get started, right? We'll go ahead and use a little bit of color here, right? Let's remind ourselves what it means for x to be an odd number. So there's a definition of what it means to be an odd number. So x is an odd number. What this implies, right, is that there has to be some integer out there, so that x is 2 times that integer. That would make it even, then plus 1. Now, some people like the definition of 2 times an integer minus 1, but they're equivalent definitions. But we're going to use the one that says if you're an odd number, you have to be 2 times something plus 1, right? Guaranteeing that you're odd. So we would write this, and this is going to use some of that notation we covered in that introductory proof video. This means there exists a number, right, which is going to be an element of the integer. So there exists n, which is an element of the integers, such that x equals 2n plus 1. So we're reading this as saying that there has to exist some integer, right? That's what this is saying. There's some integer out there such that x is 2 times that integer plus 1. And if you think about that, we're saying that there's some number out there, multiply by 2, add 1. That guarantees that x is an odd number. Okay, let's do the same for y being an odd number. So y is an odd number. Let's translate that. Y is an odd number. So this implies that there exists. Now, we can use the same definition, we just can't use the same letter, because if we said that there exists n again, well, then we're sort of implying that x and y are the same, which is certainly not one of the assumptions here. So we can say there exists m, which is an element of the integers, such that y is 2m plus 1. Okay. So we've translated our two assumptions. X is odd, we know what that means now. Y is odd, we know what that means now. Okay. Now, let's go to what we need to show here. This then is our goal, right? And we are saying then x plus y is an even number. So what we need to show is x plus y is an even number. So we've told our reader by writing that, right, that our goal is to show that x plus y is an even number. But just like we did above, we want to translate that into a mathematical statement. So we need to show, same thing, there exists a k, we're just using another letter, we don't want to reuse n, we don't want to use m. There exists a k, which is an element of the integers, such that x plus y is 2k. All right, now notice that the definition for an even number is that it's 2 times something, right? That guarantees it's divisible by 2. That's guaranteeing that it's an even number, right? So again, what we've done so far, we haven't started the proof at all yet. We haven't made any sort of logical steps or anything. We're just using the definition. So it's essential here that to do this proof, if you had to do it on your own, you would need to know what is the mathematical definition of being an odd number. We used it twice here. What is the mathematical definition of being an even number? We used it right here. All right, let's actually attempt our proof then. So our proof, right? And again, stylistically, I like to actually write out the word proof to indicate to the reader that everything's sort of up here, right? This is just stating definition so that they're aware of things that we might use. We're also phrasing our need to show, so we're aware of where our target is, what our goal is. And now, by signaling this, this is where we're actually taking those logical steps to go from the assumptions to our conclusion. All right, so let's go ahead and do that. So for our proof, let's take x plus y, and let's say what we can say that that is equal to. Eventually, we would like to say that x plus y equals, right, that 2k there. For now, though, what do we know about x plus y? Well, we have something we know about x, and we have something we know about y. So let's go ahead and use those definitions, those assumptions. So we can replace the x with 2n plus 1. We'll use some parentheses just for clarity there. And then plus, and then we'll go ahead and we'll replace the y with 2m plus 1. Okay, so we've used our assumptions. Now, if we think about it, we don't really have any other assumptions to use, right? So that sort of tells us that our next step should probably be something based on a mathematical property, a logical step, or a mathematical operation. And clearly, we can see some mathematical operations here. We have a sum. We can combine some like terms. Let's go ahead and do that. So that then tells us that x plus y is equal to, well, we can combine some like terms, 2n plus 2m, and then the 1's combined together to be a 2. Okay. Our goal is to reach something that looks like this, where it's 2 times an integer. Well, notice that everything here has a factor of 2, so we can do a little factoring, again, a mathematical operation to take a step forward. So we can say x plus y is 2 times n plus m plus 1 when we do that factorization. All right, now we're basically done because we just need to recognize that, well, n is an integer, m is an integer, and then that adding 1, that's going to keep it an integer. So we can simply do a little bit of a definition or a sort of a renaming here. Let's go ahead and just say let n plus m plus 1 equal k, right? We're just renaming this thing. And then we have x plus y equals 2k. And there we go, right? Notice that we've reached mathematically what we needed to show. We needed to show that there exists a k. What is our k? Our k is n plus m plus 1, such that x plus y equals that 2k. We've reached our need to show, and we've definitely confirmed to our reader that was our goal. We've reached our goal. We've finished our proof. And there we go. We've done our first direct proof showing that the sum of 2 odd numbers is guaranteed to be an even number. All right, let's go ahead and take a look at another example similar to this, where once again we will focus on the idea of the translation, leading through and translating the need to show, and then actually working through the proof aspect, where we'll take a series of mathematical steps to arrive at that need to show. So let's take a look at another example here. All right, so let's go ahead and try this. This is not something about numbers here. This is going to be something about functions. We're going to prove that if we have two functions, f of x and g of x, that are both strictly increasing functions, then f of g of x, the composition of those functions, is also strictly increasing. All right, so clearly the key definition in this is going to be, what does it mean to be a strictly increasing function? So let's go ahead and translate that. So we'll use, again, some color here. All right, this one, they're written as both, so we can just go ahead and translate them directly. So what does it mean to be strictly increasing? That means that if you put in a larger input, you're supposed to get out a larger output. So what this would mean, right, if we're translating that, f of x strictly increasing, right? This implies, okay, well, if we put in a larger input, so if, say, we'll just use some letters here, A is less than B. So A is our small input, B is our large input. Then f of A needs to be smaller than f of B. So if we put in a larger input, we're supposed to get out a larger output. That's what it means to be strictly increasing. Same thing for g of x, right? G of x strictly increasing. This implies if A is less than B, then f of A is less than f of B. Man, having a little trouble writing there. F of B. Okay. So we're basically saying these functions, if you put in a larger input, you get out a, oh, and these should be in G. My apologies there. Let's go ahead, just erase that, make sure we have the right notation. Then G of A is less than G of B. Okay. So some people would argue stylistically we probably don't need to write it twice. We could just say this applies to both of them. Again, when we're first starting off, if you guys are just starting with your investigation of mathematical proofs, it's probably better to overwrite things, to state all of the definitions and everything. But either way, we've written it down here. We could maybe refine it a little bit by just saying g of x has the same property. Whatever we like, though, let's proceed from here. All right, let's talk about our need to show, right? We need to show that f of g of x is strictly increasing. So we need to show that f of g of x is strictly increasing. So once again, we'll translate that. We need to show that if we have A less than B, so if we have a small input and a large input, then f of g of A is going to be less than f of g of B. Right? If we put in a small input versus a large input, we get out a small output versus a large output, strictly increasing there. Okay. Now, one thing before we actually start this proof is I'd like to just sort of contrast the definitions that we're using here, right? I mean, stylistically, this example is very similar to the previous example, but notice that the definition here actually includes an if-then, right? If we just briefly go back to our previous example, notice that here, the definition of x being odd or x plus y being even is literally just a single identity, right? It's a single equality here, right? X being odd means x equals 2n plus 1. If we're trying to show that x plus y is even, we need to show that x plus y equals 2k, right? The definition here was literally just a direct identity, almost just a straight mathematical statement. Here, it's a little bit more complicated because it's not just saying f of A is less than B, f of B. It actually has this logical operator part that says if A is less than B, then f of A is less than f of B. So actually the definition has an if-then inside of it itself. So a little bit more complicated here. All right, let's go ahead and start our proof then. So proof. Okay, well, because the definitions all focus on if A is less than B, we're going to start by assuming that A is less than B, because everything we care about is only applicable if A is less than B. So even basically our first step of our proof is to add an additional assumption, and normally that's a dangerous thing to do when you start adding extra assumptions, but in this case all the definitions we're trying to show or trying to use apply or only are important to us when that assumption is true. So we're going to get to use that additional assumption. So let's go ahead and let A less than B. So we're going to assume that A is the small input, B is the larger input, right? We're going to start from there. Okay? Okay. And remember, our goal is to eventually get to saying that f of g of A is less than f of g of B. Okay. Since we have this letting A is less than B, right? Notice we're going to sort of think about this from the inside out, right? Since g of x is strictly increasing, we can use this to saying since A is less than B, then g of A is going to be less than g of B. So we can say, it's okay to use some words here, so we can say since g of x is strictly increasing, then, and of course you could use an implies arrow, right? You could write something like this if you want to be a little fancier, right? So since g of x is strictly increasing, then we know g of a is less than g of b, right? So we're applying the definition of what it means for g of x to be strictly increasing. We're assuming a is less than b, so we automatically know that g of a is less than g of b, right? So we know that we have our g of x is strictly increasing. Now, at this point, right, we sort of want to apply the f function here. It's up to you, I think, stylistically, how you want to proceed here. You could do something like sort of renaming these to make these sort of clearer to somebody. So you could maybe, to be really, really careful, now say something like let g of a equal c and g of b equal d. So we're just going to rename those. So now we have c less than d. And then since f of x is strictly increasing, then, well, since c is less than d, we know that f of c needs to be less than f of d. Right? That's what it means for f of x to be strictly increasing. We're applying this definition to this. The only difference is that this was phrased in a and b, this is phrased in c and d. So since f of x is strictly increasing, then f of c has to be less than f of d. But what was c? Well, it was g of a. What was d? It was g of b. So this would be f of g of a has to be less than f of g of b. And what do we know, right? We said let a less than b, and now we know f of g of a is less than f of g of b. We look back up. That was what we needed to show. And so we know we've reached our target, we know we've reached our goal, and we've proven our statement. So this one here, definitely a little bit more challenging because of the fact that our definition actually has an extra assumption in it. The idea of defining what it means to be strictly increasing requires that you assume that you have one smaller input, one larger input. In terms of this moment right here, where you sort of redefine the g of a, the g of b, I think a lot of people would say that that's unnecessary. You could simply say that you can apply the f function directly to g of a and g of b, and since you know g of a is less than g of b, just basically think about g of a as your a, your g of b as your b, and you can skip this extra lettering thing. So again, maybe we were overly sort of pedantic with this, but overall, right, probably better safe than sorry since we're just sort of starting off, and we certainly have reached our goal here, which we set up back in our need to show, so we know we've accomplished what we set out to do. All right, let's turn to our last example of a direct proof here. So we want to prove that if y equals f of x and y equals g of x are solutions to the differential equation y prime plus a of x y equals 0, then y equals f of x plus g of x is also a solution to this differential equation. Now, depending on when you're sort of engaging with this video here, you may or may not know what a differential equation is. And what's sort of interesting about this example here is that you don't necessarily need to have a deep understanding of what a differential equation is or how to solve differential equations to understand how to do this proof here, as long as you understand the concept of what it means to be a solution to an equation. So one thing that I sort of want to really highlight in this example is that proving something is very different than understanding computationally this type of situation. Again, a lot of you might be watching this video without having ever learned how to solve a differential equation. Yet if you understand what it means to be a solution to any type of equation, you can still prove a statement about differential equations, even if you don't have a lot of computational knowledge about that. And that's really to sort of distinguish the idea of mathematical proofs from mathematical computation. So let's go ahead and do some translation here. So first of all, what does it mean for y equals f of x and y equals g of x to be solutions to this differential equation? Well, in general, what does it mean for something to be a solution to any sort of equation? It means that when you plug that thing in, you get an identity, right? You get something that is always true. So what this would tell us, right, is y equals f of x is solution to differential equation. What that means is if we plug in that f of x in for y, we get an identity. So we would know that f prime of x plus a of x f of x is equal to 0. So we get an identity. So we know that this is always true. So if we ever see something like f prime plus a of x f of x, we know that that is automatically equal to 0, right? So this is an identity. This is always true. Okay. If you want it to be really formal, you could probably include something like this off to the side and say that this is true for all x. I think a lot of people would also argue that if you didn't write this, the for all x, that's implied by the fact that we're talking about a differential equation. So again, maybe that's overly pedantic, but let's just be safe and write it down here. Well, we also know the same is true for g of x. So y equals g of x is a solution to the differential equation. That means that g prime plus a of x g of x. So we're plugging in y equals g of x. So we're putting in the derivative there and the original function there. That's how we're getting that. That must equal 0 for all x. Okay. Now let's translate our need to show. So we need to show then y equals f of x plus g of x is a solution. So we need to show y equals f of x plus g of x is a solution to differential equation. So let's translate what that means. That means we need to show that if we plug in f of x plus g of x, so that means we need to show that f of x plus g of x prime plus a of x times f of x plus g of x equals 0. So notice what we've done is we've replaced the y equals f of x plus g of x in for here. So we have f of x plus g of x prime. That's matching the y prime. Then we have a of x y, and we're saying y is supposed to be f of x plus g of x, and it's supposed to give us equal to 0. And once again, that is for all x. So that's what we need to show there. All right, let's see how we're going to do that. Right, so for our proof here, well, we need to show that this is a true statement. Now, certainly, and this is something to be very careful about, we don't want to start by writing this statement, right? If we start our proof there, then we're assuming what we're trying to prove, and that's going to invalidate our proof. So instead, we'll start from here, and we'll try to reach this here. Right, so we're going to be starting from this left-hand side, and we're going to be trying to work our way over to our right-hand side, right? Because this we need to show is equivalent to this. Now, could we start at 0 and work our way over here? Absolutely, right? I mean, if you're trying to show that two things are equal, you can pick either one and work your way to the other. Of course, though, we are usually used to starting with more complicated things and in our mathematical careers simplifying them. So we probably want to start with the complicated side and work our way to the not complicated side, right? But logically, you could go either direction. It's just that we're not usually used to complicating equations. We're usually used to simplifying them. So let's go ahead and start off with that side there. We can say f of x plus g of x prime plus a of x times f of x plus g of x. So what can we say that this is equal to, right? Well, this is where we're going to be making use of our mathematical steps or operations. So let's go ahead and do that, right? We know how to apply the derivative to a sum. The derivative distributes over addition, so we can go ahead and call that f prime plus g prime. And we also know that how to multiply functions. We know that that function also distributes there and there, so let's do that. A of x, f of x plus a of x times g of x. Okay, so we're saying that this is equivalent to this. We want to eventually get it to equal 0. Well, notice we want to eventually make use of our assumptions. So we sort of know that we want to gather things that look like this, and then they equal 0, and things that look like this equal 0. So we can't say anything about these two things together. We have no assumption about what f prime plus g prime is equal. But let's put this with this, and let's put this guy with this guy. So we'll just rearrange. Addition is commutative, so again, mathematical property, we can just go ahead and rearrange this stuff. F prime plus a of x, f of x. And let's just use some parentheses, unnecessary, but just for visual aid. And then g prime plus a of x, g of x. Okay, so we're saying that this is equivalent to this, which is equivalent to this. Okay, but this, by assumption, we know is equal to 0. So this is equal to 0, and this guy, by assumption, is equal to 0. So we have plus 0. Now, again, stylistically, some people would say that this is sufficient. You have these written up here, so you can just go ahead and directly change these into these zeros like that. Some people would say that maybe you should make a comment, right? So you could do something like off to the side, just include since y equals f of x, y equals g of x, are solutions to the differential equation. So you could just remind the reader that the reason you're replacing this and this with 0 is because these things are solutions to the differential equation, and that is covered back up here. Again, people would argue about whether or not that's really necessary, but again, just to be overly sort of safe here, we're including it. And then we have that this, well, 0 plus 0 is 0. So now we would read this, right? Any reader would see that this is equivalent to this, which is equivalent to this, which is equivalent to this, which is equivalent to this. So reading that, that means that this is equal to this, which is exactly what we needed to show. So we've completed it. We've gone from here. We started from this left-hand side, and we've arrived at that right-hand side. And so we have completed our proof. So once again, another somewhat different but good example of a direct proof. You will notice that all three of our examples, so we just briefly go back, look a bit different. Here, right, you were using very simple definitions. What does it mean to be an odd number? But notice it had a similar structure to our last one, right? We needed to show x plus y equals 2k. We started with x plus y, and when we ended with that 2k. Now notice that I did, just out of sort of convenience, change stylistically how I wrote it. Here, I took the time to always include x plus y written on like the left-hand side every time. So I kept writing x plus y on each line. On the last example, I went ahead and just said, let's make it a chain of equalities. Let's say that this equals this, equals this, equals this, equals this. Instead of writing this guy here, and then here, and then here, and then here on every line. Again, both are logically equivalent, but notice that since this one had more sort of writing on this, we sort of omitted that, and we just said, you know what, let's just go ahead and say is this chain of equalities, this, equals this, and so on. Again, we could have done that back over here. We could have just said x plus y equals this, which equals this, which equals this, which equals this, and then just had our chain from there to there. Okay, so there are alternate ways of writing these proofs out that are logically equivalent and valid. It's up to you sort of stylistically which you sort of prefer. Sometimes, right, it's nice to be safer like this when there's not as much writing to do, and then other times when things get a little messier, maybe it's convenient just to write it as a chain of equalities like this. Probably the most interesting of these three is our middle one, just because here the definition that we were using had an additional assumption And so we had to make sure that when we did our proof, we made use of that extra assumption. This brings us to the end of our discussion on direct proofs. In general, and you'll hear me say this for all of the sort of videos that involve different proof techniques, the only way to get really comfortable with mathematical proofs is to simply try as many as you can and read even more than that so that you get comfortable with the different little sort of minutia of how you format these proofs, how you make those sort of logical steps, and you also develop your own style that makes you sort of comfortable with how you want to write up and sort of display your logical understanding there. So this brings us to the end of our discussion of direct proofs. In our next video, you'll be looking at an alternate proof technique which talks about how to prove via the contrapositive.